Welcome. Good morning to everybody. I would like to start the second day of our international workshop of the xGMobile. My name is Luciano Mendes. I'm the General Coordinator of the Competence Center on 5G and 6G networks. And today you're going to have a very long day, but also full of innovation, full of new information. And also you're going to see some new research that are coming up here from our studies. We're going to start with an overview about how TVWS space can be used to provide connectivity in remote areas. Also have some insights about how 3GPP works and how its standardization process happens in terms of shaping the radio interface. And also you have a tutorial on security for short length communication using Bluetooth device. In the afternoon, you have a talk from FAPEMIG, which will present how the state of Minas Gerais is supporting the research on mobile communications. And you have also a keynote from South Africa that are using TVWS space to provide connectivity in low-cost remote areas. And you're going to close the day with a technical section talking about the futures and applications on 6G networks. So the first presentation of this second day is going to be opening TVWS spacing as a solution for unlicensed 6G networks. This presentation will be done by me and also by Professor Rodrigo Porto. I will already introduce Professor Rodrigo Porto. He is a full professor of telecommunication at the Federal University of Ceará. UFC, he has founded and coordinated the GTEL, which is a research center that for 25 years has been dedicated to the development of wireless mobile telecommunication in Brazil. Through his research, Professor Rodrigo has contributed to the evolution of radio access technology since the second generations. And he has published also several scientific publications, patent in Brazil and abroad, and more than 40 completed the masters and doctoral supervisions in telecommunications. His current research interests include the evolution from 5G to 6G, dynamic spectrum management, digital inclusion, and artificial intelligence. So I will start the presentation. The following Professor Rodrigo will join me. So we started to develop TVWS space here at Inatel around 2015 as an answer for a demand for connectivity in remote areas. There is an economic aspect for providing this connectivity, which is actually how we can improve the digital transformation of sectors such as agribusiness, mining, and also provide service for border control and environment monitoring and also disaster monitoring. So that was the initial motivation. We started using the UHF and the VHF bands to provide this kind of digital transformation of audio's applications. And we have this very simple idea, which is not new. It was already established in 1998 with the idea of cognitive radio, where we have a spectrum that is more or less empty in some places. And you have this kind of opportunity where you can deploy a secondary network and provide connectivity using this vacant spectrum without paying any kind of license. So the idea here is to remove the barrier of being part of action to get the license of a spectrum so that you can deploy a service in a given area. So since this is a secondary network, it has not the primary use of the spectrum. If there is a DTV signal that is deployed later on in this area, the network must be able to sense the presence of the signal and move itself for another frequency. So that means that this network must be smart enough to identify the interference and adapt itself to the new environment. And it needs to do that by itself without any kind of human interaction, right? So it seems simple, but there are a lot of requirements in terms of waveforms and also MAC layer to allow it to happen. The first is that you cannot use RF filters because RF filters it locks the frequency where you can operate. So you need to be free to move to the spectrum, right? So you need to transmit without any kind of filtering. So that means that this signal, this unlicensed 6G signal, must have a very low out-of-band emissions. And you need to deal also with the predistortion, since you are using power amplifiers that can also introduce a lot of interference in the surrounding bands. Also, the MAC layer must be able to sense the presence of this interference and change the position of the spectrum on the fly. So those are the new mechanisms that you need to add to a unlicensed 6G network, and that's what have been working the last few years. What are the challenges, right? So I mentioned some, but let's see what happens if you have here a system that works as a secondary network, and that's using the legacy waveforms that you use in 4G or Wi-Fi, for example, which is OFDM. So OFDM is a very interesting waveform because it can deal with the multipass. It's a very efficient waveform for mobile communication, and it can deal with this kind of frequency selective channels and time variant channels. But if you do not use a RF filter, what happens is that you have a lot of energy leakage because the waveform has a abrupt interruption from one symbol to the other. So there is a huge transition from one symbol to the other, and these transitions causes this kind of sink shape spectrum, which leaks energy to everywhere. So if I use this waveform without RF filtering, and then there is a primary user that starts to use the channel, you can even detect that user. You can clean the spectrum, but there is still a huge interference here because of this waveform that has been used. So you cannot use this kind of waveform to provide this kind of service. It was done in the past. IEEE 802.22 tried to do that with, it was basically WiMAX, but then they shaped it a little bit to work as a cognitive radio network. But the OFDM mainly hinders the use of this feature. So that's the main feature that you'd like to have in this kind of network. So what you can do, we can change the modulation scheme, you can change the waveform, and then design a new waveform for this kind of applications. So that's what we have done. So now you have a very smooth waveform here that has practically zero leakage. And in this situation, if you detect the primary user, and then you clean the sub-key areas where the primary user is located, you can coexist without any kind of interference. So controlling the waveform is a key feature for providing this kind of service. So the main message here is, okay, you cannot have a network for this kind of application that use legacy technology. You need to have new technology for this purpose. So here it's also very important to have the spectrum sensing here. So this here is a measurement that you did here in Santa Rita. So here you have like 3 channels, 3 TV channels. Inatel owns those channels, so those channels are for our use. And you deploy your network here using 2 bands. And then we realize that there is a 30 signal here in your channel, right? So that's my band. Somebody was using it, right? If you look to the Inatel Mosaico, which is the database where they say which channels are occupied, which channels are free, you're going to see that this band here is completely free. If you trust only that database, you're going to deploy your network over there, and the quality of service will be terrible because there is somebody here transmitting that you didn't know. So spectrum sense is very, very important. So here's what you have achieved so far in terms of results. You are testing here basically the coexistence between our network and a digital TV. So what you're seeing here is the spectrum of TV signal. And here it's our signal. You can see that they are surrounded the TV signal. Here's the TV signal reception. So there is no interference at all. Now we change to OFDM. You can see that the out-of-band emissions increased a lot. It happens outside of the spectrum, but also inside of the spectrum. And you can see here that the digital reception is completely compromised. So here you can see that you can coexist without any kind of filter if you use the proper waveform. So GFDM, it's one that you have been used so far. There are others. That's not the only one. So you're not advocating the use of GFDM itself. We're just showing that the requirement that you're showing can be achieved with new waveforms, and you can see that the coexistence is possible. And here's the spectrum, right? The spectrum sensing. What you are seeing here now, let's just try to play it. Yeah. So you're seeing here now, our signal here is occupying the entire bandwidth. Here you have 4 DTV channels, right? And then now you're turning on a digital modulator that will insert a DTV signal into the receiving signal. The network must be able to detect the DTV signal, as you can see here, and then it cleans the spectrum, so there is no interference at all. So you can detect that on the fly and be very responsive to the presence of the primary signal. So we implement all those technologies in a new radio access network. We deployed this network here in Santa Rita already. Next year, the first semester of next year, you're going to deploy it also like in Ceará, in a small city in Ceará called the Quixadá. We have designed everything from the physical layer, so all the blocks here have been redesigned from the scratch, and they are using the MAC layer from 5G, but you add all the blocks that you needed to make this spectrum sensing and this spectrum relocation, and this is it's what is implemented now. You are almost achieving TRL 6 now. It's almost done in terms of testing in field. And everything here is implemented using SDR, so it's a real-time network that can be deployed in the field. And the idea here is to use this new frame that you have here to coexist with TV stations and add this period silent to allow the system to detect the primary signal if they come after the band is designated for the secondary network. And with that, you can deploy this network coexist with any kind of DTV signal. So those are my main conclusions, is that the TV white space can provide this solution for the connectivity gap in Brazil. We need to use new schemes. You cannot try to use the coexistence with future schemes using legacy technology. And you need to use the spectrum sense to assure that you have a proper coexistence with the DTV signals. And the systems also work with TV 3.0, so there's not a problem with the future DTV signal that is deployed here in Brazil. So just, this is my part. I would like now to invite Professor Rodrigo to continue with the presentation. Esse aqui volta, esse aqui é o pointer. Isso.
So thank you very much, Professor Luciano, and thank you, Inatel's xGMobile Competence Center for the invitation. It's a pleasure to continue the excellent presentation by Professor Luciano on this discussion about TV white space as a solution for unlicensed 6G networks. So I'll be talking specifically about one component of the system, which is the geolocation database, okay? Professor Luciano has already introduced me, thank you. So what is the geolocation database? Well, first of all, let's consider, oops. Okay, 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 thank you. First of all, let's have a look at TV white space as a system. Of course, it has its radio side. It's heavily radio dependent. That's a radio access technology. So, but in the radio aspect of it, you find the usual pieces of equipment, such as the base station, which has all the usual equipment, such as amplifiers, the antenna system of the base stations that you see over there, and the customer premises equipment, okay, of course, installed at the customer premises, and this, of course, makes the whole radio part and closes the radio link so that you can offer the broadband data access, the internet access to the customers. So this is, of course, an essential part because it's a radio access technology. But beyond that, this is also a system that has logical components because these nodes, they need to talk to each other. And then you have the CPE. The base station here is being called by its formal name, master device. You need a gateway that interfaces the radio system with the wider internet. But then you need a fundamental component that works as an orchestrator of the whole system, which is the geolocation database. Because remember, this is a system that works on a secondary basis, opportunistically, so it can't use spectrum that is already used in a given location. So this geolocation database is a crucial node that authorizes or not the radio equipment to use spectrum in a particular location. Okay, so it automatically will authorize the radios to use that in that particular location, in that particular GPS coordinate, to be able to find the pockets or the white spaces within the TV broadcast spectrum that are available for secondary use in that particular location. So that's it's a sort of orchestrator, okay? And it has a protocol, of course, to communicate with all those nodes and make the whole system work on a coherent basis. So what are the key components or the key concepts to make this geolocation database to work? So I will lay out now 4 key concepts that I hope you will understand, if you're not familiar with this concept, how this geolocation database works. The first one is the idea of exclusion zones. So we start by borrowing information from the Brazilian national regulator, which is Inatel. And Inatel has an official database in which we find the information about all Brazilian primary TV broadcasters. We find information about where they are, their GPS coordinates. We find information about the antenna system, the power levels, etc. So we borrow this information. That's the first step. And around those transmitters, we create those exclusion zones. So this is a protection for the TV transmitters. Within those exclusion zones, there's no possibility, of course, of placing a TV white space transmitter. And we can calculate or estimate those exclusion zones based on regulatory parameters, and also based on a worst case, in which the green circle here, in which we use the maximum allowed power for the transmitter, and a nominee directional antenna as a premise. Or we can, if the information is available, we can calculate a more fine-grained contour. It's the blue one here, which takes into account the actual power that is being used, that may be a bit less than the maximum allowed one, and also the antenna pattern, if that information is available in the database by Inatel. With that, we start by creating all over Brazil those exclusion zones. And this is the first step in protecting the primary transmitters. That's our key goal here, okay? We can't, of course, create any type of interference with the primary transmitters. And this is the first building block. The second building block is the other way around. We now look at the TV white space transmitter. This picture here is showing a simulation in a well-established propagation modeling tool in which we place a TV white space transmitter in a famous beach in the state of Ceará called the Jericoacoara. And then we set up a power level and we analyze how the radio wave propagates and spreads throughout the region around the transmitter. And these are very well-established models. This is a very well-established scientific and technical field of propagation modeling. What's the point here? It's the other way around. We have to be able to limit the transmit power of this TV white space transmitter so that it does not reach any exclusion zone operating in the same channel. Okay, so you understand, exclusion zone on one side and the limited power on the other one, so that the radiation, the wave propagation, does not reach any exclusion zone in the same channel. With those two components, we guarantee that there will be no interference to the primary transmitter, which is a precondition for TV white space to operate under any regulatory authorization by Inatel. Okay, with that, we more or less orchestrate and solve the radio part. We need now to look at the database part. The database itself requires a protocol, and hopefully and fortunately, there is a standardized protocol by the IETF called PAUSE, Protocol for the Access of White Spaces, specified in this RFC 7545, which specifies a set of messages and expected responses for the radio equipment, such as the master device or the base station and the geolocation database, to talk to each other, to exchange parameters. For instance, the radio equipment will ask the geolocation database the list of available channels in a given location. How many channels, which channels, and which power levels can be used in a given location. And this is done by an API in which they can exchange those messages and get responses. So the orchestration takes place using this protocol. This is very good because with this protocol, which is standardized, equipment from any maker in the world can talk to our database. So that's very good. It's not a proprietary solution, it's a standardized solution for the protocol part. So with that, the nodes can talk to each other in the network and exchange the necessary parameters to authorize or not, depending on the availability of spectrum in a given location, the use of spectrum of TV channels on a secondary basis. And finally, the fourth concept is the implementation of the database itself. And here we have brought some innovation. We opted to employ blockchain as a database technology because it's distributed. That's good for a Brazilian scenario, which is a large country. So we created this API that talks to the blockchain. Blockchain brings interesting properties of security, auditability, reliability, fault tolerance. And this is also an interesting property of the solution we have implemented. So all of that has been implemented. And now I can bring you some practical results that we got from the project we are running in partnership with Inatel. So one thing that we did to make the primary transmitters, the TV broadcasters, more comfortable was to, nonetheless, those propagation modelings are well established. We performed a few measurement campaigns to validate those models, to experimentally bring data to show that they are reliable. Of course, small calibrations are part of the problem, but we did extensive measurement campaigns around the city of Fortaleza, in the metropolitan area of Fortaleza. We went to different regions, mountain-based regions, rural ones, on the beach, urban regions. So we collected data from different types of environment and we validated the model. We have the data is available for the TV broadcasters to check so that the modeling part is reliable. That's important because it's a model, but nonetheless, they are reliable models and we have brought data to subside to support that claim. Another important part of our project was to hire an external party to validate the protocol implementation, the PAUSE protocol implementation in our API. So a third party that is not involved with the project development was hired to validate the internal consistency of the protocol implementation. They did manual and automated tests, sending messages, getting back responses, checking if the responses were the expected ones. So an exhaustive testing suite to check that the PAUSE application, the PAUSE implementation we did was compatible with the original IETF RFC. Another, still trying to make the concept more practical, we did Wi-Fi prototyping of the same protocol. So that's the protocol, that's the database. Only the radio part was implementing using programmable Wi-Fi cards, so that we tested the protocol using Wi-Fi instead of TV white space. And finally, the integration of our geolocation database with Inatel's TV white space suite, I think, was the most important part, because now the excellent suite of radio equipment that Inatel has developed is integrated with the database, so that we can bring the equipment from Inatel to any place in Brazil. And we have a demonstration in the state of Ceará shortly at the beginning of next year. And they can automatically, in any given location, check the availability of channels, get this information, and based on the automated part that you saw, the radio is very, very agile, the radio from Inatel. They can select which channels, and more than one channel if possible, because they can actually make this type of carrier aggregation in any given location, okay? Finally, we also developed a tool that is publicly available if you want to go deeper into TV white space. There is this website. It's written in Portuguese, so it's fiquespectro.com.br/mapa. I will show some screenshots of the tool, but it's publicly available if you want to try, in which you can do several analyses about the potential of TV white space in the Brazilian landmass. So the first screenshot shows the location of all Brazilian TV transmitters with their respective exclusion zones. So this is a zoomed out vision of the whole country, but you can zoom in and see a particular transmitter, and with its contour. This is one transmitter, one TV channel in Fortaleza, at Fortaleza. Okay, this is based on the Inatel's database. But more interestingly than that is we can check the availability of spectrum in the Brazilian territory. And in this particular screenshot, remember, we have up to 50 TV channels in Brazil. And the purple color here is around 45 plus channels, okay? So you see that for the majority of the Brazilian territory, we have 40 or plus unused TV channels. And this is a very scarce and important resource that is being inefficiently used in most of the Brazilian territory. More interestingly, so this is the general picture. Here is a filter. We have a filter in the tool that in this filter is 30 or more channels, and this gives about 83% of the Brazilian territory with 30 or more unused channels. It's about 180 megahertz of unused spectrum that could be very useful for internet broadband access. You can also check, there is another possibility is to check the availability of coverage using mobile communications, 4G and 5G. And again, there are a big chunk of the Brazilian territory, this brown curve here, which is limited connectivity even by mobile broadband. And the most interesting thing is that there is a strong correlation between these areas in brown, in which connectivity is limited, with the amount of available channels. So if you just see the correlation, the amount of available channels exactly in those areas where connectivity is mostly limited, even by wireless and mobile communications. So there's a huge opportunity here to fill in the gap of unconnected small villages and farms, because the spectrum is there exactly where it is mostly needed, where people have more limited options. We know there is a satellite-based company that is actually taking advantage of that situation, a foreign company. But we could be using Brazilian technology also to fill this gap. So it's up to the regulators now to allow this technology to be really implemented in practice. We're basically waiting for the authorization of the Brazilian regulator to really put in place this solution as a commercially viable option. Okay, so just mention our sponsors, nick.br, the UK government, which has also funded this project, our great partner Inatel, and to my co-PIs, Dr. Carlos Silva, Professor Thiago Nóbrega, and my fellow students at UFC who have, of course, been involved with this project. Thank you very much.
So we do have time for questions.
Very impressive, thank you. My knowledge is from 2008 through 2014 about TV white spaces when I was doing research on cognitive radio networks. So as you know, the TV white spaces were released so that the investors and also companies can use them. I'm sure you know about the super Wi-Fi concept, you know, introducing the Wi-Fis in these TV white spaces, and it didn't take off. So when you look back, it kind of like, I thought it died down because the TV White Space Alliance, the leader was Apu Modi, was one of our PhD students at Georgia Tech. So he moved out and he does something else. So I'm really surprised that suddenly a huge activity here in Brazil. The reason for that was that the TV providers, the program providers were somehow upset that these new area of TV white space users may cause interferences for their programs. That's why many people or you know, startups and other companies could not penetrate the market. So what is the reason that I'm surprised and very impressed, by the way. So all over the Brazil, you are trying to introduce this. So what changed in the meantime?
Luciano, maybe I give just a short answer, and then you can you complement. I think there is a specific, large countries. You're talking from the USA perspective. Well, USA would probably be also a candidate for TV white space. So large countries like Brazil, now we have this problem of digital inclusion. That's becoming more and more a sort of social and political issue. There is a pressure, it's more a strong push from even politicians to fill in this gap of digital inclusion. And there is a significant amount of people in Brazil because the country is large, the population is large. There's an estimate of about 20 million people with limited or no connectivity. So it's a lot of people. So there is this political push in a sense. And the solution, the conventional solutions, based on mobile connectivity and optical fibers, they are slow to deploy because of the challenging economic model of these types of situations in which you have a small village or a remote farm, so the business case doesn't really close as well. So that's what I mentioned. There is a well-known satellite company, Starlink, that is filling this gap. There is a market. And then we together with Inatel are trying to we think that there's a solution for, at least for the Brazilian case, that is very well suited to our situation right now. Of course, there is regulatory hindrances. You are correct. The broadcasting industry is skeptical. But besides the geolocation database that I just mentioned, Professor Luciano can also talk about the sensor capabilities of the radio. And by putting the two things together, the modeling and the prediction of the models together with the sensing capabilities of the radio, we really have a robust solution that can basically guarantee that the broadcasters will not be, they will not face any type of interference, not significant one at least. Please, Luciano, you can complement.
Yeah, just to complement, we have received Dr. Apurva here several times. We are Dr. Apurva, the president of the WSA. Yeah, I know him quite closely. Yeah. And we actually did test a lot of equipment that he brought here from Canada, from US. And the big problem with the approach that was done in the past using 82.22 is actually that the network was not designed for this scenario. They just took the WiMAX or Wi-Fi and tried to use it. And that was the biggest problem. And at that case, the broadcaster was quite right to be skeptical because the waveform was not ready for that. The physical layer was not ready for that. And if you do not use a proper RF filter, the interference is going to be huge. So they should be really, really careful regarding that. What you're proposing here is not to reuse that technology, but redesign everything to this application. So you start from the scratch with the requirement of coexistence, spectral agility, and fragmented spectral allocation. And your physical layer is completely new. There is not from FDM or LTE or 5G or anything else. It is a radio access network designed for this environment. And with this approach, you can assure that coexistence can happen. I have showed here our spectrum side by side with a DTV signal without any kind of interference and without any kind of filtering. So that's not a mad idea. I'm not crazy about it. It's really working.
I think I like. Hello? Yeah, I like your answer, but I think what we could say is that during those times, we did a lot of spectrum sensing algorithms. And, some of them was working very well and some not. But now we have all these AI native, we were discussing yesterday, these new techniques like this ISAC, right? The integrated sensing and all that. So we are much further out now in technology. So you are revisiting the problem, saying you can do much better spectrum sensing and also keep those TV white spaces free of these interferences. And now I understand. So I think it's a good idea.
Exactly that point, yeah.
Right.
In the last 10 years, you have evolved a lot in terms of
No, it's good.
waveform and the AI and the spectral sensing. And you're much more, now I think you're ready in terms of technology to deploy the system.
I like the idea. So it's a good idea to revisit really well. Good.
Thank you. I guess you do have time for more questions if you have. That's the tricky one now.
Thank you. Thank you, Luciano. Thank you for the presentation. You commented now that the physical layer is not a reuse of any previous technology. It's totally a new one. But I suppose there are some similarities with is used in 4G. Could you extend a little bit? What are the differences or similarities?
Well, the idea of heavy frame and resource blocks is still there, right? You do have some pilots for spectrum estimation, right? And also you have this table that makes the dynamic allocation for the users. So this idea from 5G, 4G is still there, but the frame itself is quite different. For example, the subcarrier bandwidth, right? In 5G, you have the base 15 kilohertz, and then that goes up to 40 kilohertz. And that makes the signal shorter, the CP even smaller, and the robustness to large delay profile is weaker. So you did it the opposite side. Instead of increasing the bandwidth per subcarrier, you're decreasing it, right? So it's short, smaller subcarriers in terms of bandwidth, longer data symbols, larger CPs, more efficiently used to combat large range networks. So this is one of the difference. Also, you're not using FDM at all. You're using GFDM in this case. GFDM, yes, is implemented in running real time. Everybody is skeptical regarding the receiving GFDM because of the interference, ICI, ISI, but you solve that problem. It's running real time on a conventional CPU, and the performance is quite good. I'm trying to set up the demonstrator here for the afternoon. Let's see if I can do it. From the coding, we are not using LDPC, are using Polar. You're going to talk about 3GPP later on, right? But the standardization procedure to 3GPP is a little bit crazy. I really do not understand why you have two coding there. But you are using Polar coding, and the performance in terms of absorbing the interference from the TV signals into your system is quite high. So they can actually coexist without causing interference and holding the interference from the TV. So that's really good because of the polar code that they're using. So those are the main differences in the physical layer. On the MAC layer, it's basically what you can see now in 5G, right? The only thing that you did is that you insert a cognitive cycle that pauses the transmission from time to time to do the spectral sensing and the spectral reallocation if needed. So there is a silent period in the frame where nobody's transmitting, and the nodes can sense, and then later on, using the control channels, transmit the result of those sensings. And at the base station, it decides that there is some primary using that signal, it coordinates to change to another frequency. So those mechanisms is also added over the 5G MAC layer. From the LE3 above, everything's the same. I think, yeah, time is up. Okay, so let's applaud Professor Rodrigo for the presentation. Thank you.